to share the screen of the presentation. Okay. Awesome. All right, so I think let's get started. We are doing this for both online and also in person. So the people who are on Zoom, can you hear us?
Yes.
All right, thanks so much, and please mute yourself. Awesome, thank you. We are getting started. So today we are very glad to have Kiran from Meta Reality Lab to join us to give a talk titled, to talk about the project area at Meta. And Kiran is a system architect at again Meta Reality Lab. He's one of the leading person behind this project area, which is the Meta augmented reality glasses project. And he will talk a lot about the journey through the years and to having this amazing product to be released soon. And so I was told that the Meta the area will be kind of open source soon, right, to the general public. So I'm very excited to hear a lot about this project from Kiran. Kiran got his PhD from University of Maryland, and we are long-term friends. We had an internship together at Qualcomm back in the days when we were PhD students. So without further ado, let's give the floor to Kiran.
All right. Thanks, Meet. Thanks for the kind introduction and inviting me here. It's been a long time. 10 years back, we interned together. I'm super excited to be here to talk about Project Aria. It's a new tool that we built in Meta to enable egocentric AI research. As Mia was mentioning, I'm Kiran. I'm a systems architect, which means I'm someone who puts things together. And we build these classes in a team called the Surreal Vision team. We are a part of Reality Labs research. It's one of the research arms within Meta. For today, I'll be going over what is Project Aria, why we specifically built the device. It's a lot of smart glasses out there, so I'll motivate why we had to build another one. And then get into some technical details on what's capable on these devices, what we have packed in this device. And then introduce the research kit that we share with academic partners, like Dr. Zhang's team here. We have glasses that we give out to our partners to do or enable egocentric AI research. And then specifically, I'll touch upon a couple of research opportunities in the space of efficient AI, something that I'm collaborating with Dr. Zhang. And then I want to spend a good amount of time on demos. So I'll go over one Jupyter Notebook demo that talks about like the data that's collected, the kind of tools that we provide to process the data, spatial AI capabilities. And then time permitting for the audience here, I can show a live demo of streaming from the Aria glasses to a laptop, where we can run models in real time, things like eye tracking, hand tracking, and SLAM. So you can walk around the room and see how your processes are localized. And then I definitely want to open up the forum for Q&A towards that. So the talk should be around 30 minutes. The rest of the time is for demos and Q&A. All right, so just to quickly introduce where we come from. So we're coming from the personal computer revolution arc within Meta. And the last half a decade, we've seen the space or the personal computing era go from mainframes to desktops and PCs to mobile. And then the next step, we believe, is going to be personal computers in the form of AR, VR, and wearables. That's the vision for the team. That's the vision for the organization. And we're building devices and tools to enable it. This is Doug Engelbart. If you don't know him, he's considered as one of the founding members of human-computer interaction research in the US. In fact, like the mouse goes back to his times from SRI. He's one of the inventors of the mouse. So he made a very profound statement. If you were supplied with a computer that worked all day long and was instantly responsive to every action you had, how much value could you derive from that? At Meta, in our labs, this is the vision that we're working towards, a new generation of human-computer interface where you don't have to type, but rather the systems understand what the humans are perceiving and how do we close the loop with the agent fast. But there's one fundamental building block that's needed for this technology, which is for the tech to understand what the user is doing, like what they're saying, what they're seeing, what they're touching and interacting with. And this needs to be available always on. And this technology building block is what we're calling as always on machine perception. So ARIA as a device is designed to enable always on machine perception research. In parallel, we also see the revolution in AI. So you see with the increasing capabilities of autoregressive large language models, that you can say that modern AI is quite accessible to everyone. So you don't need to be an AI researcher. You have chatbots that you can prompt to and make things happen. But how do we make it useful in the context of human-computer interfaces? That's an area where we are invested in, and we call that as contextualized AI. So what do we mean by contextualized AI? So it's a combination of the human context, what the user is interacting with, the physical world, what they're seeing, what they're talking about, like, the audio, the video, the rich multimodal environment that the human context is captured in, and also like interaction with our digital services like Google Photos, Instagram feed. So all of this combined together is context for the human. That's very unique because it's from the egocentric perspective. And then we combine it with a strong reasoning engine. So in today's LLM world, you can think of this AI as a large language model or autoregressive large language model. And then the context as a tokenization of the user's reality, right? Like, so you have physical objects, the user is seeing, say, for example, I'm seeing a laptop and I'm gazing at me. All of this gets captured into a narrow context window. So the combination of these two is what we are defining as contextual AI. And we want to push the frontier on this. But however, when we started this project, we found there was a gap in today's wearables to understand this rich egocentric context. And I'll explain why. If you take a look at this video, this is one of the videos captured on the POV camera on the ARIA glasses. So there are a few salient things that I want to call out. Like typical user scene with glasses is extremely diverse. And to capture the environment, you need really high resolution sensors. For example, if you want to understand what the user is reading, you need high resolution megapixel cameras. And then the list of activities that the humans are engaged in is quite diverse. So unlike autonomous driving, where you have a fixed task, take a passenger from point A to point B. In egocentric AI, the tasks are not well defined. It's all over the spectrum. So we need to be able to capture a very rich environment context to make this happen. And when we looked at commercial devices out there, we could not find one that would suit our need for the rich capture for egocentric activities. So the devices out there either sacrifice on the sensing capabilities or on form factors. So for devices like HoloLens and MR product lines, they have the right set of sensors, but it's quite bulky. So you can't wear them always on, and it's not always available to you. And MR headsets might not be safe for things like, for driving or other use cases. And then there is the other spectrum of devices, which are more wearable. So they're all-day wearable like GoPros or smart glasses, but they typically sacrifice on the sensor capabilities. So you have a POV camera, but it doesn't capture audio at the spatial resolution you need, or personal tracking or other inertial sensors. So there was a gap. So we identified this, and a couple of years back, we introduced the Project ARIA device, which is primarily a research platform inside of Meta. And now we are opening up that platform for university partners and closed research partners in industry. And I want to emphasize that Project ARIA glasses themselves are not consumer products. So it means you're not going to be buying them off the shelf, but they're not prototypes. They're not research prototypes. It's really a platform or a tool, initially for teams inside Meta to build and understand what AR sensing would look like. And now we are opening up this tool for academic partners. And you can go to those URLs to figure out more about our privacy policies, what we do within Meta, and what's available to academic partners. Before I get into the technical details, I just wanted to share one motivational video of a research we did with Carnegie Mellon. This use case was resonated very closely with me, with my aging parents who are losing vision. I found this particular tech that CMU built very, very relevant. So let's walk through, or let's go through a quick. I should have put this one on to play. A quick.
For years, I've gotten around with the assistance of my guide dog, Flirt. I love and depend on her dearly, but a guide dog is not a navigation system.
Juice bar is on your right.
NavCog can change that.
There is a ramp, 140 feet.
What we're working on is a turn-by-turn assistive technology that we've developed at Carnegie Mellon University. We teamed up with Reality Labs and Meta and started using their Project Aria research glasses to build a 3D map of the Pittsburgh International Airport. The maps help the user figure out where they are without having to rely so heavily on external beacons. This is huge because it makes NavCog scalable.
NavCog gives me the freedom to go where I need to go.
You have arrived.
It really helps me regain my independence.
Okay. Fine. Okay. I'll get into more of the device technicals later, but I just wanted to introduce like what are the sensors we have packed into this device. So it's a full sensing modality, what we believe is relevant for future AR glasses. So it has 3 scene cameras that are looking at the environment. It has 2 low resolution positional tracking cameras that are VGA resolution. They're global shutters, so you get very good timing of that. There's one 8 megapixel scene understanding camera. It's much higher resolution, which allows for running some more tasks, like for example, object detection kind of tasks. And then there are a couple of eye tracking cameras that are facing the user side. They used to get the gaze vectors to figure out where the user is looking at. And then there are 7 spatial microphones. That's a spatial array, which allows us to capture spatial audio. It has inertial sensors, GPS, Wi-Fi, Bluetooth for connectivity. The device ships with a Snapdragon 835 SoC, and it's a mobile class SoC that allows to do compute on the device. It has 128 gigabytes of local flash if you want to store the recordings on disk. And then more importantly, it has a 2.5 watt-hour battery. Typically, that's not the kind of battery you would see on wearable devices. It's a pretty heavy battery, and that's why the arms look very thick. But this allows us to record for close to 2 hours on a nominal recording profile. So we have a lot of recordings we capture to understand the user data. And typically, the device is meant to be operating for 2 hours. But if you go really, really high resolution capture, then the recording time comes down, both in terms of space and battery life. So that's the specification on the device. And then from the software side, by the way, these devices are like wearable, so they're on your head. So you have to be very careful about thermal design. When we designed the device was meant to be operating at a thermal design power of 1.4 watt. What that means is as long as your compute and sensors don't consume more than 1.4 watt, the device doesn't get hot and doesn't throttle. Otherwise, it starts throttling and dropping data. To enable that, we ship the device with 15 well-tested profiles, which makes sure that when I say profiles, these are configurations of the sensors, the frame rates, the resolutions, the number of audio channels. And this provides the users the ability to select a specific profile for their research. If you're interested in audio research, you would choose a 7-array microphone, maybe lighter rate on the sensors, camera sensors. So you have the option to trade off what you want to record, what you want to stream. And we also allow for customization of these profiles, depending on the research needs. The other capability that's very important for us from a research perspective is the ability to synchronize multiple devices, because there's concept of distributed machine perceptions. If the audience in this room is all wearing Aria glasses, they should have a better perception of the environment. And if they can share it, then you can build more smarter algorithms in a distributed setting. But for that, we need a common time base, right? So this Aria devices ship with a protocol. When we connect over Wi-Fi, we can synchronize them with sub-millisecond accuracy. Here's a video of one of my colleagues, I guess, playing in our lab. And this allows us to do multi-view captures to allow dynamic scene reconstruction tasks. In a similar vein, we also have synchronization with third-party devices, things like OptiTrack systems. So the technology is called timecode. It's used in the video film industry to synchronize audio and video. We use the same technology to synchronize to multiple extraneous rigs. So here's an example of one of the users collecting data from their ARIA glasses. It's synchronized to an OptiTrack system. Because timecode is a standardized technology, many devices like GoPro support it, and so does the ARIA device. So you can synchronize ARIA devices with other devices. The primary use case for these kind of captures is with egocentric view, you really don't know what the user is doing. You can see their hands, but you don't get that full perspective. But if you have an extraneous capture, like an exo capture, that allows for strong ground truthing. So we have been using these kind of ego exo captures to collect ground truth, to get labeled data for egocentric tasks. And these can be also made mobile because we have it working over Wi-Fi. Now I'll jump into the research kit that we offer for academic partners. So the research kit is, in summary, like a collection of our software tools that we ship with our glasses. So it's glasses, a mobile companion app. We also provide hosted machine perception services. These are services that are hosted in Meta's backend. So if you're collecting data, you can upload the data to our backend. We process the data, give you things like eye gaze vectors and SLAM poses. So it's very useful for research if you want to build higher order reasoning, assuming you have everything co-localized. So we make the computer vision part easy so that you can focus on the contextualized AI bit. And then it also ships with an SDK, both C++ and Python. Python is going to be released soon, and then you'll have sample apps to play around with. In this talk, I will not have time to go over our open science initiatives. We've released 3 big data sets, some open source tooling around it. We also have some models that we open source, like face blurring model called Ego Blur. So if you want to release your own data set captured using ARIA, we provide that model to blur out the faces. So you can use that before your data set release so that it's consistent with the IRB requirements in universities. All right, and then this is very important. Again, like because it's a partner program, although we are Meta, the data that the universities collects belongs to the universities. So we don't have any ownership on that. We're interested in the research that comes out of it. So we want to be plugged in, but we don't have any ownership on the data or the model. That's a very important caveat to note for this program. And we're all good as long as we follow community guidelines and IRB guidelines that are set up by the university. Right, and then it's kind of a quick snapshot summary of what the research kit is. It's the glasses, a companion app on Android, which allows you to look at the device health, the battery life, Wi-Fi connectivity, GPS. It allows you to control the glasses, so you can start and stop recording from the phone, and then you can set different recording profiles. We also provide a desktop app, which allows you to stream data. So you can use that for debugging purposes. Things that you cannot do with a mobile phone are shipped into a desktop app. And then last but not least, this is the research kit machine perception services. So these are backend services. Here's an example where the users have uploaded data from probably a couple of conference rooms or maybe their home. They get uploaded to Meta backend. We build maps out of these, and we provide the maps as metadata that can be used along with the data. So you don't need to do any of the SLAM stuff. We provide a service to do localization stack and point cloud. So the technology behind this, we have tested this for the last 5 years. It's the one that ships in a lot of headsets that Meta makes as products. And then we also provide eye gaze vectors. So those gaze vectors can be localized in a 3D map. So you can actually know what the user is gazing at instantaneously. This is one of the things that we are pushing towards efficient AI, because instead of understanding the whole scene on the RGB perspective, which is a lot of pixels, you can focus only on the pixels that the user is fixating on. You can filter out saccades and just look at what they're fixating. And if you try to understand what the user fixates on, that's already a lot of compression, if you will, right? You're not sending the entire RGB frame, but only a crop of it. So these are examples of few of machine perception services that we have today. We are planning to provide more for you to build on top of. And then I already talked about the SDK. It's both C++ and Python SDK. It allows you to very quickly stream data from the classes. I'll be showing a live demo, so I'll skip over this slide. I'll be showing a live demo of the SDK. In terms of what we can enable with the SDK, I have three motivational examples that from research that's been done in my labs. We have one of our researcher who's using the glasses wireless streaming data to his powerful workstation. They're running ML models in real time. So it's combining an object detector with 3D point cloud information you get from ARIA. And using that, he's able to do 3D scene registration for objects. So that's one example use case. We call it indexing because you can index every object in the scene. And then this is more of a, I like this because it's kind of an eye candy. This is where we use our SLAM point cloud and take the magnetometer data on the glasses, and you can see really the dynamic magnetic field. For example, that's TV, so you can see the magnet from the TV speakers and how the magnetic field revolves around it. So things that are not just perceptible to the human eye, like computer vision stuff, you have all of those non-inertial, non-vision sensors that can also be captured and registered onto a SLAM frame of reference. Yeah, it's also a testament to how stable our SLAM maps are. The last use case is similar to the first one, but this is more large scale, where with the trajectories we get from the ARIA devices, we run a CubeRCNN model. It's a 3D bounding box predictor model, monocular, and we combine those predicted bounding boxes over time to create persistent 3D objects in a map. Again, tech that you can just put together because we have the SLAM poses, and CubeRCNN is an open source model. You just have to do temporal filtering and registration, and you get this kind of 3D visualization. Okay, so that's kind of what we offer as a research kit. So this is like today, if you get these devices, you should be able to get these capabilities from us. Specifically, I wanted to talk about some of the challenges that we see in the AI efficiency space, and that's very relevant to the research that we're collaborating with Dr. Zhang's team. So to motivate that, I just wanted to call out like the data volume that's captured in these devices. You have two SLAM cameras, you have an RGB sensor, you have eye-facing camera. These are all dense captures of pixels. And then microphone arrays are also very expensive in terms of data rates. So if you take nominal compression into account, we're literally recording 0.9 terabytes of data per day per person. That's a lot of data from a small device. And first recording it's going to be challenging. It's going to hit thermal limits. You're going to hit space limits as well. Now, just as a thought exercise, if we multiply this over 100 interacting people, say in a room, over a year, that's close to 31 petabytes of data. And that's a lot of data for us to even persist at a large scale company like Meta. And I think from a contextualized UI use case that I'm motivated, if you believe like you're going to see an arc of using the current day LLMs as the AI, then we're limited by a context window of 8,000 to 30,000 tokens if you want to keep the latency minimal. So we cannot shove in like petabytes of data into the context window. That's not going to work practically, just from a latency perspective. Even if the context windows become larger with newer and newer models, latency would become a bottleneck. So I think the ask for the community here, which works on efficient AI, is like we need new methods of compressing this egocentric AI data. Raw pixels themselves wouldn't scale out. So we're looking for research collaboration on how do you tokenize all the observation that you see from these classes. And that's a research area that we are spinning out. And if there are teams in your labs which are looking into these domains, a combination of multimodal LLMs, that's a great and ripe area to work on for egocentric research. All right, with that, I'm close to my 30 minutes mark. I want to go to a demo, but before that, if there are any questions, I'm happy to take it. Yeah, I'll let him go first.
For the consumer side, I know Meta has released recently Cloud with Rebate, released a consumer side product. And then people have used products and service and as an insider, I'm just curious about like what's your thoughts on this products and service before people say that Meta will be able to
Okay, first, I cannot comment on the product side of things, but privacy is something that we take very seriously in this program in ARIA. So we know that, I mean, the premise here is always on machine perception, right? For products like the Ray-Ban stories, we're always having the control to start and stop the recording. But if you want to go towards always on machine perception, then, like you don't really have control over that. The sensors are sensing. So we have to move away from the paradigm of capturing raw pixels. It has to be more on-device compute. So whatever leaves your glasses has to be already a token, something that doesn't capture PII. So that's the direction in which we want to go. Actually, that's one of the collaboration points. Like we want the data to stay in the glasses as much as possible. And we want to bring it to a point where it's minimally, the data has to be minimized to a point where it's useful for the task. And for machine perception, you don't necessarily need like all the raw pixels people's space they can work on, right? So that's a research area that we're investing on heavily. Things like on-device AI, federated learning. As long as data lives in the devices, we can address a lot of privacy concerns. But this is specifically from the research side of things. Yeah, he's going next.
So coming from the systems perspective, so I'm working on a systems research. So you said that computation is happening on the glasses, right? Not on the cloud.
For the SLAM examples that I showed, they were all on the cloud. All the real-time SLAM capabilities, I guess. But nothing prevents us from running it. Like I'll show examples of it running on the edge. The examples that I showed were on the cloud.
So given that you also have edge computing, and so how do you think the convergence of HPC and AR, high performance computing and AR? So do you think is there any active research going on?
Yeah, no, edge compute is a major part, right? I think when you say edge, it also is, it's going to be more distributed than what it is today. So glasses themselves, I mean, it's all thermal for these devices, right? So before you run into battery limitations, you'll run into thermal limitations. The glasses will get hot. So you want to do as little as possible in terms of capture. Phone will be an important part of your ecosystem. So you will stream to the phone, do a little bit of compute there. And then phone to edge to cloud, that's an existing ecosystem already. So in terms of AR, the challenges there are like, how do you get multiple devices to interact with each other? That has to be done locally because there's going to be a latency challenge otherwise. There are a lot of low latency challenges on the edge compute. In terms of AI, specifically like contextualized AI, which we spoke about, I don't think we can ship all the data to the cloud. It's not practical, just from a communication bandwidth perspective. So we want to do low-level reasoning on things like the phone to begin with. Later on, maybe they can move to glasses. And for the more cognitively harder tasks, we'll push it to the cloud. That's the vision.
So I'm also like in the videos or in the previous demo videos, I don't see any object and any kind of, it's basically a segmentation boxes or maybe audio guidance. So how about like we can see that there are some AR objects and similar like that, right?
Right.
There's some AR objects handling. So to render those things, you need a very high compute power.
Correct.
So for that, how it's
I think, so just to clarify, these glasses are more like smart glasses. They don't have a display in them. So that's why you don't see a concept of a display. But I agree, like rendering is a very expensive operation from a GPU perspective. But even more power hungry is the display. So I think we need to solve the display first, then go into the rendering stack, and then talk about, how do you integrate those things together. I mean, right now, if you look at the consumer devices out there for AR, things that can do form factor AR, they're very limited and they're quite bulky. and majority of the weight comes from the display. So if you're able to shrink the display, it becomes smaller, then we can get into the rendering challenges.
And then you mentioned that it has powerful edge capabilities, right? So what sort of compute power does it actually have? Like, does it have a GPU for processing and things like that?
These classes are themselves, they just have a Snapdragon SoC. It does have a GPU inside. We don't expose that because we're not using it for any rendering capabilities. When I say edge, I'm talking about laptops, phones, and other peripheral devices, not the glasses themselves.
And how does it interface to the phone, through Bluetooth or
Wi-Fi. yeah.
Is that expensive in terms of battery power?
It is. Wi-Fi is actually one of the more expensive modalities for comms.
But we have to use Wi-Fi otherwise.
No, you also have wired cable if you want to do your research, but then eventually you want to have a tetherless experience, right? So the idea is compress as much as you can on the glasses. Bluetooth is definitely less power hungry. Modern Bluetooth can support 500 kilobits per second, but
My question is basically how much data to the phone does it send right now in the compressed state? Like, how much data does it collect in real time and send to the phone?
so in the example, the streaming example that I showed with one of our researchers streaming the data here, right? This will be around 2 to 3 megabits per second. And that cannot be done over Bluetooth. It has to go over Wi-Fi. But this is just scene cameras and SLAM, right? But if you want to do audio, that's more. We have, once you get these devices, you can profile. I think 20 megabits per second is reasonable from a bandwidth perspective. After that, the devices get hot. Does it answer your question? Yeah. Right. I don't know if there are any questions. Oh, yeah, go ahead.
So, for the last question, can I understand the question of like, how to tokenize like each, for example, CV and annual kind of things, and put that into a time series, and we observe like a long time. And so we processing the time set data, reasoning what users doing. So can I understand the question that?
Yeah, that's one of the things that we want to research. We don't have the tech yet, and we don't know what the right representation for this multimodal tokens should be.
Yeah.
And also, these models are very expensive to train, so we want to first fully understand the design space before we go and train these models.
So, but it's kind of time series data especially. So
It's a time series, or you can think of that as, most of these transformers are sequence learners, right? I wouldn't call it specifically time series because you can also like tokenize the pixel space, linearize it, but sequential learners.
Oh, thank you.
Yeah.
Yeah, so I was curious. So when you mentioned that this one is not, this one not meant to be for the sales, right? It's just for research.
Yes.
So how much are you actually interested in? Give me, for example, in the temperature low. For expect that the temperature maybe a focus for maybe for the general people. When you have to sell this product out, right? For now that is research, how much are you interested in controlling it?
No, I think as long as it's on the user's head, there are certain regulations that we have to follow.
Okay.
So it will be whatever constraints are there on the product side, we have to honor it because it's a safety issue, right?
Right, okay, good.
I think like that's why I wanted to emphasize it's not really a prototype. You can think of this as a platform. So it has to honor all the, like, for example, wireless, it has to honor all the FTC regulations. We partner with a lot of universities in Europe and other places, right? So each of those will have their own regulatory constraints on what kind of bands you can use. So we honor all of that.
And I guess that since you don't do much computation in the main node that you have to use to control them would be the same.
Correct. It's frame rate, resolution. Yeah, it's a trade-off between BPS and temperature.
We have 10 minutes after.
Of course, yeah. There's a breakout session. Right. Not sure if there are any questions on.
We don't have any specific question online.
Okay. So in that case, let's shift gears and go to a demo. I wanted to figure out the mouse. Yeah. So this is a notebook that we ship along with our open source repo. So there's data collected, and I wouldn't have time to show the videos themselves. But let's look at some of the examples that we have. Yeah. So this is a rendering of our SLAM map. So you see, this is the same video that I showed in the presentation. Oh, by the way, can folks still see my rerun screen on Zoom?
Yeah.
You can? Okay, cool. All right. So these are capabilities that we provide. Like once you say you get our glasses, you have recordings, you use our machine perception services to generate these point clouds. We provide like sample apps to run things like point cloud localization. So this is the point cloud of the room that's captured from a user's kitchen. And you can see the point cloud 2D to 3D correspondence, the points being rendered on the two SLAM cameras. So these are the two SLAM cameras. And we are rendering the corresponding point cloud on these two SLAM cameras to see how consistent the edges are. It's a very important debugging step before we start going into the real-time SLAM parameters. And you can see that the user's head pose or the SLAM pose moving in the map. So it's all world locked. Okay. And then if I showed the trajectories already, we can skip the calibration part. If I just run it. So extrinsics are basically telling you how the cameras are oriented on a glass. So the two SLAM cameras, the RGBs, so the relative location of those. And it shows you like the corresponding RGB rendering for that. So this allows you to kind of visualize the 2D, 3D in one frame of reference. So it's a very important debugging tool that we have. If you're doing your research and you see your models are predicting something wrong, you plug it into these tools and see, okay, hey, I'm looking at this object, but it's predicting as instead of a laptop, it's predicting as a table. Then you can see probably the eye gaze went on the other direction, therefore it's predicting as a table. So that's an important debugging step before we can deploy models in production. And then the very last tool is on eye gaze. So I can load it at time. For folks interested in 3D vision, there's this new tool. It's called Rerun that they have released. It's an open source package, and a lot of our toolings are built on top of that. So it's a shout out to the Rerun team. It's an excellent tool allowing to visualize multimodal 3D vision data. So let me do a final run to show what it's capable of. So you can see your RGB camera in a fixed frame of reference. And you can also see the gaze vector at what the user is gazing at. So it gives you a very strong visualization prior on what you're doing. So you can see that when they're serving food, they're looking only at their plate. And these kind of capabilities are, in our mind, like this is the way to get at compression. It's going to be very hard to feed all the point cloud data or all the RGB data into, even if you're doing multimodal LLMs, into a model. So just using this, figuring out like what the user is interacting with or looking at, and compressing that data to visualize the 3D, to compress and create tokens would be a good way to do efficient AI. Yeah, let me not spend more time on this. I want to go to the live demo. How do you want to do the live demo? I can show it for folks here. It won't be available on Zoom. Yeah, I think that's yeah. Okay, sounds good. So I'll stop screen sharing. For folks in the call, maybe I can send a screen recording of that later. And then you can visualize like what the real-time streaming capabilities would look like.